So welcome everyone to today's seminar. Today we have Jen Sobeck, who is an associate scientist at Caltech IPAC and plays an active role in the next NASA flagship mission, the Nancy Grace Roman Space Telescope. She currently serves as the lead system scientist for the Roman Science Support Center at IPAC. Dr. Sobeck also oversees the microlensing system operation MSOS pipeline development team that will process the data from the Roman core survey, the Galactic Bulge, time domain survey as well. Her research focuses on the chemical and kinematic characterization of stellar populations within the Milky Way and local group. So thank you very much, Jen, for accepting our invitation. And sorry for the delay. You may start when you're ready.
Okay, thank you. I want to preface this by saying that I've actually been sick over the past few days, and so my voice is not what it should be. And so please let me know if I'm unclear. Please feel free to interrupt. Don't hesitate, and I will try again to restate what I have been saying. But I wanted to thank you guys very much for this invitation and this opportunity to speak about Roman. This has been my job for the past almost 3 years now, and it has been a labor of love, so to speak. But I'm very excited to talk to you guys about the next NASA flagship. I also want you to know in my spare time, in addition to, and there's very little of that, but in addition to that, my job and working with NASA, I try to also be a mom. I'm a mom to two kids who are 4 and 7. So they keep me very busy, and hence why I was preparing this presentation probably about two this morning. So thank you very much. So I'm going to give you just a brief overview of the Roman mission and the work that we plan to do. Please know that Roman is a collaboration, first and foremost, and it's a collaboration of many people across the United States, as well as many people across the world. And we have a variety of international partners to whom we are greatly indebted for all of their expertise, both scientific and technological, and they have really helped to shape the Roman mission and what it has become. So I want to start this with our namesake, Nancy Grace Roman. I want to state, first and foremost, that this is the first NASA flagship mission to be named after a woman, and rightfully so. Nancy Grace Roman was NASA's first chief of astronomy. She actually joined NASA in 1959 when the agency was just barely starting. It was only 6 months old. She championed space-based astronomy, which eventually led to the Roman Space Telescope. But interestingly, really truly, I think Nancy Grace Roman can be credited with Hubble. And so not only did she help to advance space-based astronomy and general astrophysics knowledge, but this and push these priorities in the mission itself, she really helped to develop the Astrophysical Science Division, which plays a huge role within NASA HQ today, and makes NASA not just only doing payload and rocket launches, right, but also really have a heavy science focus. So we're deeply indebted to her. And so I want to talk about Roman as a whole right now. Basically, Roman was conceived in the 2010 Decadal Survey. The Decadal Survey is a process that the US undergoes once every 10 years, right? In which we examine the science priorities. And so there's a panel that's formed and basically says, representing a variety of expertise across the United States. And they decide what the science priorities should be for the next decade. And so the panel, of course, met in the late 2000s, the aughts, so to speak, and then decided that a Roman should be one of the next major missions that they should take on. Roman is interestingly a NASA mission that I really want to highlight because not only is it on budget, it is actually early. And it was really important for NASA to prove that we could deliver such big, huge missions at cost and within budget, but also, in a time scale that was at least on time. And then due to a variety of reasons, which we can talk about later, we're actually pushing the mission and we're trying to have it launch ready by September 7th. So just a few months for now. The latest that we plan to launch is May 2027, and this will be from Cape Canaveral in Florida. Roman has a lot of just basic science themes underlying it, right? We want to tackle and look at dark energy. We want to perform an exoplanet census. We want to look at the expansion of the universe and combine all of these science themes to truly perform transformational astrophysics. Interestingly enough, Roman is a survey telescope, and it's the first Class A, the first flagship mission to be a survey telescope. We've had other missions like TESS and Kepler, but they weren't flagship. So when you think of Hubble and when you think of JWST, these are primarily PI-led, primary investigator-led, or team-led types of efforts. But Roman is a survey telescope. And with that, we're actually going to have still a section of time set aside for PI-led astrophysical surveys, right? And in fact, we just had our first call for this PI dedicated time. It started in November 2025. That was when the call was issued. And then we actually had call proposal submission just a few weeks ago in March. And I really hope that you all were able to not only consider submitting for Roman time, but potentially did submit proposals. Please let me know. So here you can kind of see an overview of our what we would call our flagship portfolio, right? All the flagship missions that NASA has, launched over the past several decades. And so, it's a very nice thing to think that, there's this continuity, right? You had Nancy Grace Roman pushing space-based investigations, especially at a time when NASA, that was not the focus, right? We were, trying to launch, do manned spacecraft missions, right? And we were trying to get to the moon. But Nancy Grace Roman was there in the background pushing these science missions. And in fact, she is known as the mother of Hubble. And so what you can see is a whole kind of view of the missions. Let me see if I can move this out of the way real quick. Oh, I'm not hard to, it's not working. Anyway, but a variety of missions where you can see that we had Hubble, Andra, Spitzer, Webb, and now Roman. And the nice thing is that the continuity is based off the discovery, right? So the discoveries of Hubble, right, and the discoveries of Spitzer really pushed forward this interest in having very precise near infrared imaging and spectroscopy that led to to the Webb telescope. Similarly, for Roman, there were a variety of discoveries with regard to exoplanets as well as dark energy, and that really prompted and motivated the construction of the Roman telescope. So you really have this kind of nice thread that you have discovery, and then it promotes another idea, and then finally eventually leads to fingers crossed another mission that NASA undertakes. And so you have just a really nice little quote from Nancy Grace Roman saying that scientific research and engineering is a continuous series of solving puzzles. So I wanted to give a few cartoon diagrams but just to kind of, describe Roman and where you could see its niche and how it fits in the context of the other NASA missions, right? So on this left-hand side, you have the mirrors, so you can see Hubble, Roman, and Webb. Obviously, Webb has the dominant primary mirror size, being very large indeed, around 6.5 meters, right? But Hubble and Roman are actually roughly about the same size, about 2.4 meters in diameter. But their purposes couldn't be more distinct. And so what here you see on the right-hand side is the field of view, right? And you can see that both Hubble and Webb, their field of views are overlaid across, a particular scene from the galaxy. And then you see that in contrast to Roman and the enormous field of view that it actually has. Wavelength-wise and coverage-wise, when you think about the instrumentation on board these missions, you can see how Hubble really truly spans a huge range in wavelength, right? Going from the very deep ultraviolet and far ultraviolet, in fact, through the visible into the near infrared. Roman, of course, sits in this, kind of mid visible to near IR range. And then Webb takes it from there and actually goes from the near infrared all the way out into the mid infrared range. And so you see the complementarity in the missions, right? But the goal is, of course, is that you can use the data in a complementary fashion, right? So that you could pull objects and events and analyze them across this huge range of both wavelength space as well as mapping. So hopefully this will work. This is just to give an idea. Oops, oh, no, sorry. Let's try that one more time. This is my technical difficulties. Here we go. And this is just a nice kind of, rendering, comparing, again, those field of views, right? So you can see that Hubble is focused on this particular area. And then we're zooming out. And now here's the Roman field of view coverage. And this is an image, a ground-based image, which you can see that we've overlaid those two fields of view. Again, to kind of just give you a rough idea of Roman and its power and what its portfolio is actually like. Roman has a 300 megapixel camera. It has an advanced coronagraph on board. It is originally scoped to be a 5-year primary mission. We plan to launch this, like I mentioned earlier, and with fingers crossed in September 2026. But we will launch it to an L2 orbit. And the primary mirror is about 410 pounds. This is interesting because I contrasted Roman with Hubble, right? Saying that the primary mirrors are, about the same in diameter, but the weight of the Roman primary is so much less than that of Hubble. And that's just technology, right? It's just technological advances enabling that reduction in weight for the primary mirror. And because of this, we were able to, scope this mission differently and have it have a wider field of view. The F ratio, of course, is so much faster for Roman than it is for Hubble. And that's all due to advances in technology. So now I want to go a little bit into depth about the Roman instrumentation and walk you through aspects of both the coronagraph as well as the wide field instrument. So the coronagraph instrument is a technological demonstration instrument, and that's an important distinction. What that means is that though the instrument itself, which was built at JPL with a variety of industry partners, is at the highest class and the highest technological level, it is only scoped initially for a 90-day operational period. So it will not actually be taking data over the full 5-year primary mission. The wavelength coverage is in the visible, as you can see, from about 0.4 to 1.0 microns. But the interesting thing about this is that it is a contrast imaging instrument in which you're blocking out the primary star, and then you're trying to image then its companion exoplanets. And so here you can kind of see just some very nice technological renderings of the coronagraph in the background. And the thing about the coronagraph is it's almost a pathfinder of sorts. We hope that this level of technology will be improved upon, but for the upcoming Habitable Worlds Observatory. And the focus, of course, of that observatory is exoplanet detection and detection of Earth-like or even smaller types of exoplanets. The chronograph is really truly, this embodiment of high technology, right? It has numerically optimized precision fabricated chronograph mass. It has large deformable mirrors for high order wavefront control with thousands of pistons. So you're going to actually be adjusting these mirrors in real time. And then it has electron multiplying CCD detectors for low flux photon counting. Because even though we have blocked out the light from that primary star, still being able to detect it with any significant signal to noise of those exoplanet companions is quite challenging. And when we block that primary mirror, primary light from that star, from the parent star, it's called digging the dark hole. Interestingly enough, this digging the dark hole will actually be performed in real time, and it will be performed here at Caltech IPAC. So we have like a mission operations center, and we have an uplink through Goddard and through the various NASA channels, and then we actually will control this instrument in real time to make sure that we are really truly blocking that parent star light and trying to capture the light from the companion exoplanets. And so here are just kind of some of the critical technologies that I just mentioned for the coronagraph, but just views of them right now. And you can see the ultra precise wavefront control, the large deformable mirrors, the high contrast chronograph mask and what they actually look like. Here's a view of the ultra low noise photon counting detectors. And then all of this is going to be used to, generate these coronagraph images, which, by the way, does have some other instrument modes, which I can get into later if you would like. But then, allowing for the blocking of the parent star light and then the imaging of the exoplanets. Whoop. Now we're going to go to the wide field instrument, which is truly the workhorse of Roman. This is the primary science instrument. It has both imaging and spectroscopy, and it will be operating over the full 5-year baseline mission timeline. It has 8 imaging filters with a bandpass that spans approximately 0.5 to 2.3 microns. It has 2 slitless spectroscopic modes, a grism and a prism, with a bandpass that encompasses about 0.8 to 2 microns. And it has 18 near-infrared detectors. These are Hawaii 4RG detectors, which are about 4,000 by 4,000 pixels per detector. So the imaging capability and quality is absolutely enormous. I do want to contrast this just slightly with Euclid. Euclid is our a companion mission launched by ESA. It has already been in operation now for a couple of years and is about to have a big data release, which is very exciting scientifically. Euclid itself is a huge wide sky imager. The main contrast between Euclid and Roman, there are a few, but Euclid actually has Hawaii 2RG detectors. So there's a little bit of a difference with regard to the actual image quality that is going to be coming from Roman and for Euclid, but they do have complementary purposes, and I want to highlight that. So let's get into the nuts and potatoes of the wide field instrument. So on the left here, you can actually see those 18 detectors. You can see them numbered. Each of the detectors, of course, was vetted for quality control wise, along a whole variety of axes, right? Just to make sure that the detectors themselves are viable and of space quality, right? There's a number of rejects that we actually go through. You fabricate many and then choose the best, of course, as you guys might imagine, right? The numbering scheme is a little interesting. I don't know who came up with this, but it's the one that we're working with right now. Really importantly to point out to you, the quality of these, the images received from these detectors, they've been vetted numerous times, but they really truly do have low background, low persistence, low, dark count rates, really high image quality data. There are slight differences, of course, and we will count for any of that odd detector behavior and that distinctive detector behavior in our calibration and removing that from the final science quality images that we present. So it's like I mentioned, it's a focal plane array. It's of 18 detectors, 6x3 array. There's a field of view of roughly about 0.281 degrees squared, so 0.8 by 0.4 degrees. There are gaps, and you can see that even on the left when you look at that picture or that focal plane array of the detectors, right? The spatial sampling is 0.11 arc seconds per pixel. This is similar in nature to the spatial sampling that you would get from the HST wide field camera 3, especially in the near infrared. You get a little bit better performance in the UV from Hubble, but truly just considering the field of view and all other improvements, enhancements of Roman, the image quality almost surpasses that. If it actually kind of does for that of Hubble. So you're going to have guiding, which is going to be interleaved with science data collection. You have 8 filters, as I mentioned, that span 0.48 to 2.3 microns. And we have a filter wheel in place. And so in the middle of this slide, you can see the filter wheel and you see the various filters. So F87, F146, F184, F158, that's like the H band. You can see the prism, F129, that's like J band, F106, F62, and F213 is like akin to K band. And then there's the grism. The filter wheel is quite the behemoth. It's really a monster. It allows, of course, for this data taking, but being, the behemoth and the monster that it is, we actually have a limited lifetime turning on this filter wheel. So we are limited by the number of turns that we can perform on the filter wheel. So we actually optimize over that when we think about surveys and how we acquire the data. And then the cooling is just passively cooled to cryogenic temperatures. The thing I'd like to point out to you is, of course, the coverage and the throughput of our various filters and dispersive elements. So on the left, you can see the coverage, the wavelength coverage for each of the 8 filters there. You can see the throughput. Um, there's fairly even performance across most of the filters. You can see F62, which, by the way, was the last filter to be added to the Roman mission. The performance there is not quite up to the other filters. We, of course, will compensate that, and we've been, informing investigators that, indeed, it's nice to have this blue filter. There's obvious overlap and connection with Hubble that we want to maintain with this particular filter, right? But the performance is slightly less. And then there's a nice, so you have these narrow-bound filters, the F62, F87, F106, and so forth. And then we have a huge workhorse filter, an F136. And you can see it's an extremely wide bandpass. On the right, you can see the spectroscopic elements, the coverage and the throughput. Again, the GRISM is a little bit more highly sampled and a little bit higher of a resolution instrument as opposed to the PRISM. The PRISM was actually spectroscopically for dispersive elements added last, but the PRISM has a bit bluer coverage, which of course, can all sorts of advantages, right? Thinking about, for instance, metallicity and so forth and so on. So these are the capabilities of all the various filters and dispersive elements. Okay, so I mentioned that Roman is, a survey instrument. How does this break down? How do we begin to conceptualize this? And so the thing that we thought of doing, of course, is core community surveys. And so the core community surveys are basically designed to address all the foundational and motivational questions underpinning Roman, right? The things about thinking about probing dark energy and dark matter and trying to understand the demographics of cold exoplanets. And so basically, we put together these core community surveys. It was a community-led, community-driven process, right? Where we had these panels. We had them for each type of broad survey that we thought of. So, a broad survey that was focused on, kind of dark energy and, large, large scale mapping concerns, right? One thinking about, again, probing the universe at large spatial scales, but using different types of indicators, right? And then one trying to really truly understand exoplanet demographics, but using a microlensing technique. And so it took about 2 years for, basically the committees to be assembled. Again, trying to pull from a whole range of expertise across, not only the United States, but throughout the world, right? And then, soliciting feedback. So there was a period where we opened it up regardless of country, right? We said, please, how would you, what would you focus on in these broad scientific areas? What are your scientific interests and concerns? And so we opened it up for both an initial, call as well as a final white paper call. And we took hundreds of submissions with regard to how we should operate and conduct these surveys. And then the committees kind of distilled all that, isolated the main priorities, and then actually decided how we would implement these surveys. So as you can see, we received input from more than 1,000 community members and more than 200 institutions across the world. And we're grateful for this because we really believe that the surveys that have come out of this process are absolutely unparalleled. So here is what has come out. So we're mapping the universe, as I mentioned, in very high resolution, primarily in the near infrared wavelength regime. And so there's 3 main surveys: the high latitude wide area survey, the high latitude time domain survey, and the Galactic Bulge time domain survey. And what you can see here is just a mapping, where you can see the galactic plane, right? And then this very small area along the galactic plane focused towards the inner galaxy. It's represented by an orange dot. That is actually the Galactic Bulge time domain survey, and I'll get into what that means in just a second. And then, there are small red dots again on this view, and you can those small red dots plus a slight pink dot correspond to the high latitude time domain survey. And the big swaths in blue and dark blue and light blue, that represents the high latitude wide area survey. So let's get into some of the details. So for the high latitude time wide area survey, basically, it's the big map. That's what we affectionately call it, right? And we're exploring dark energy and dark matter and everything that makes up the cosmic web. And so this is a nice cartoon diagram, kind of, explaining what the survey will actually look like and how it will be performed over the 5-year baseline mission. And so essentially, you can see there are a variety of tiers. So there's a wide, medium, deep, and ultra deep tier of data acquisition. The wide tier, obviously, self-explanatory, being covering about 2,700 square degrees. It's a huge survey area for Roman. And I'd like to point out, not for Euclid. Euclid will cover much, much broader swaths of the sky. The wide area survey will be performed primarily in the H band. So this is F158 filter, right? And it will probe to a depth of about 26.2 in H. The medium tier, still fairly broad at roughly 2,400 square degrees. This will be a multi-band type of imaging process, so YJH, where we expect to probe to depths of about 26.5 in Y and 26.4 in J and H. And then we're also going to perform a follow-up GRISM survey of this area. And we'll use not only is there scientific data and scientific exploits to be found in the imaging data, but that imaging data is absolutely necessary for the slit spectroscopy. And it helps us decontaminate and actually extract individual objects for the GRISM acquired data. So the imaging data serves two purposes there. We will go deep and ultra deep and, very obvious targets, right? That we're focusing on, for instance, Euclid deep field, right? Trying to get, probe to very deeper depths, right? And really truly trying to put together and assemble a data set that will be used for cross collaboration purposes, right? As well as broad scientific exploitation purposes as well. The deep and the ultra deep fields are, very small in nature, about 19 square degrees and 5 square degrees. And again, you can kind of see this, idea of, we're even probing in Z this time, and we're adding that particular filter, right? And we're going to very, very deep depths. The deep will have a GRISM component to it that will be complementary. Ultra deep will only have, imaging. And as you can see in the cartoon diagram, it's 520 days that we've allocated to this particular survey, and we're acquiring this data throughout the course of the 5-year mission. Here's the high latitude time domain survey. I mean, we call this the cosmic movie, but basically, as you can imagine, we're looking at high latitude areas, regions of the sky, right? And we're doing very frequent data acquisition, right? We're trying to look for supernovae and their companion galaxies, but distinguishing those supernovae. We're looking for other types of transients, right? And we're scanning the variable near infrared universe. We're hoping to do this, of course, just to sharpen our view and our understanding of the cosmic expansion, right? We believe this will yield about 20,000 type 1 supernovae. We hope to perform these kind of cosmological studies all the way out to about Z equals 2.5, maybe Z equals 3 potentially. We're going to probably acquire 100,000 transient light curves, right? And we're going to do this through, like I said, just repeated data acquisition and creating deep stacks. There is both a wide and a deep tier to this particular survey, and you can kind of see how these are laid out with regard to both imaging as well as the GRISM data acquisition. There's a northern and a southern actually component to these things where we're focusing on these fields, right? We hope to probe to depths, hope to perform data acquisition in R, Z, and Y, and we'll keep on doing this on a cadence of roughly about 5 days. For the deep tier, slightly different filter set is going to be employed, right? Slightly different, cadence of acquisition for those filters, right? But it's still at a 5-day repetition type of cycle. Again, there are northern fields and a southern field. These survey will receive 180 days over the 5-year mission, right? And again, it's scattered over the course of the data taking is scattered over the course of the 5-year mission. And then finally, the Galactic Bulge time domain survey. And we call this guy the treasure hunt. We're going to classify thousands of exoplanets, discover solar system analogs, and hopefully uncover fresh stellar physics with over, I would say that's an underestimate, more than 200 million stars. We expect to see about 100,000 exoplanet detections, right? We hope to uncover about 1,000, perhaps 2,000, depending on estimates, bound and free-floating planets. And then we hope to determine the masses of about 100,000 red giant stars. For the Galactic Bulge Time Domain Survey, it's a single about 70 to 72 day chunk performed twice a year. And it's actually going to be observations will be taken at the first few years of Roman, then there will be a break, and then there will be observations taken at the last few years of Roman. These high cadence observations, right? These ones that are both at the beginning and the end of the 5-year baseline mission we'll look at both acquire imaging data, primarily in the F146, that wideband filter, right? And then there will be accompanying photometric data acquisition in F87 and F213. And it's an incredibly rapid cadence. So it's 6 fields centered roughly in the inner galaxy, really, truly, almost slightly just offset from the galactic plane itself, slightly offset from the galactic center. And it's 6 fields, that you're acquiring every 12.1 minutes. And you're doing this in F146, and then you intersperse that with F87 and F213 data acquisition. There will also be a little bit of low cadence, data acquisition. And then finally, we hope to pair this, and this will be a feat, I tell you that, with some GRISM snapshot observations. This GBTS survey will take 438 days over roughly 10 seasons, right? But that span the entire 5-year baseline mission, but obviously when the galactic bulge is up. Finally, so we had these 3 surveys. They take about roughly 70 to 75% of all the hours allocated for Roman, all the possible observational hours, right? But there was a call within the community to say, hey, we have this beautiful imager, right? This beautiful wide infield imager. Please, there was a white paper actually put forward that said, please image the galactic plane, right? And so there was a special committee convened rather late into the process, probably about 1.5 years ago, that undertook just a study to see whether or not this was worthwhile. And if it was, how would we go about performing this type of study? So with a very small amount of time, roughly about 3 to 5%, right? We've decided to conduct a galactic plane survey, right? Where it covers roughly 3,400 full moons. I really like that image because it gives you an idea as to the size, right? It's about only 30 days in nature, so you can kind of compare that to the previous surveys, which were several hundred days, right? But you're going to map at least 600 to 690, 700 square degrees, right? Within this galactic, and you can kind of see how the fields are laid out across the plane. You can see it covers basically a small region along the midplane, and we scan pretty much the extent of the Milky Way. And then there's a larger kind of swath that focuses on the inner galaxy towards the bulge region. There is also a time domain component, and these are highlighted in blue there. And this is where we're going to really truly try to get repeated observations at very fast cadences, about 11 minutes for some areas, about week level cadences for other areas, right? And then we're going to follow up these kind of areas with some deep, either imaging or spectral data acquisition. And here, of course, the science is unlimited, right? I mean, you're not only thinking about exoplanets, you're doing stellar characterization, stellar astrophysics, looking at star formation regions, and of course, capturing transits. All right. So I hope I have impressed you with the number of data, not just, what we're going to be doing, but just the wealth of data that's going to come out of Roman. And I really want to start to dig into that and how we're going to help you use it. So if it isn't clear now, both from my abstract as well as just the talk title, Roman is a big data survey, right? And so here's a really nice cartoon diagram. And what you kind of see is on the left here is Hubble, in the middle is JWST, and on the right is Roman. And what you have, represented basically in kind of this pictorial form is, the daily downlink rates and daily download rates from each of these missions, right? Where you have Hubble at about 2.7 gigabits per day, JWST at about 58 gigabits per day, and Roman at 1,375 gigabits per day. So you can really see Roman is just this workhorse. To give you another idea as far as, compare and contrasting, and I'll hit this point a couple of times, right? HST over 30 years has produced 172 terabits worth of data. Roman in 5 years will produce 20 petabytes worth of data. Again, I hate to drive this home so much, but it's just being proud of Roman, right, and what we're going to hopefully accomplish, fingers crossed. But just preparing everybody just for the wealth of data and preparing everybody to work in a kind of survey environment. I think normally scientifically we're so used to either being members of small teams or small groups. But obviously that's changing for a variety of reasons, and we could definitely talk about that. But the era of not only big data but big surveys is here, and so we're hoping that within your particular scientific interest, your scientific niche, you're able to use this survey data and extract what you need and perform some really great science. And so again, talking about this kind of this view graph emphasizes the comparison between the two archives, so Hubble versus Roman. And then, of course, compares the daily download link rates. And just to let you know, it's already starting, right? So, embedding the Roman instrument, we go through a variety of testing and processes where we're just really exercising a whole bunch of the instrumentation, machinery, and we're doing it. We've been doing it for years, actually, right? And so again, you're getting, hit with these bullet points of, hey, what is the HST archive, how much it's ingested, how much the JWST archive is ingested. And now what this middle panel represents is it's called WFI TVAC, which is basically, integration and testing, right? And so we have a variety of TVAC processes. We're putting through the instrument through its paces, measuring, responsivity, doing a further characterization and analysis, right? Just from TVAC, we're at 600 terabytes, right? And through all of INT that took place at, our industry partners at JPL and at Goddard, we're over 2,000 terabytes. So the data is here. I just wanted to kind of give you an idea of what we're dealing with. So we rely on the Deep Space Network to acquire all of this data. Is a beautiful framework that exists across the globe, where we're relying on a variety of international partners to help us even communicate with the telescope. We have two different ways to communicate with the telescope and to actually downlink information from the telescope. But doing this at such data volumes, really, truly, it's a concern, and we're thinking all the time how to optimize over this, and it's a technological feat in itself. And so here I've just kind of broken down the various surveys that I just mentioned, right? Thinking about the number of exposures, the number of times that table needs to be updated a little bit with now the current figures, but you're getting the idea of just the data deluge that is coming down from the spacecraft. We're thinking about our the data downlinks roughly being around a terabyte per day, right? But we really truly could hopefully get up to 3 terabits per day if necessary. We're especially thinking about that if both the wide field imager as well as the chronograph are operating at the same time. Okay, so how do you deal with this data deluge, right? What tools have we put into place, and how do we help you do science, right? And so there are a whole variety of things that we've kind of put together to kind of use a cheesy word, but an ecosystem, right? But really, truly help users get used to Roman, to prepare for Roman, right? And then to actually begin to exploit Roman data. And so here I've kind of, on the right, kind of just listed what, the science centers that have been helping out with this. So we have Space Telescope Institute, right? They're known as the Science Operations Center, or the SOC, right? And it breaks down what the SOC will do. So they're going to do WFI exposure level processing, WFI high level processing, primarily for the HLTDS and the HLWAS surveys, right? The archive, the massed archive sits at Space Telescope, right? And then they also have provided a data analysis environment that I'll speak to you about in just a second. There's Goddard, as you can see in JPL, and they are our operations centers, right? And of course, they are vetting and spacecraft performances, giving us real-time monitoring and tracking, and doing real-time spacecraft control, actually. And then there's where I sit, which is IPAC, which is known as the Science Support Center. And so we have put together proposal and grant management. So if you just submitted a proposal, it came through the Roman Telescope Proposal System, which is a platform that we created. We're going to do WFI high-level processing for both microlensing and spectroscopy. And we're the ones to process some of the coronagraph data, as well as be a pass-through for JPL. And we also will help to control the deformable mirrors, as I mentioned earlier, through ground-in-the-loop type of manipulations. So there's that. That's the ecosystem itself. Now, here are some of the tools and what we have available for you right now. So there's extensive Roman documentation, but we're working to improve that all the time. If you go there, you see something's not clear, please put in a ticket. Please tell us. We will improve that documentation. It is community driven. We have proposal tools. There's the old familiar stalwart, the APT, which is both the stuff of dreams and nightmares, right? But it's being improved for Roman. We have an ETC, we have the RTPS, we have a number of other tools. There's data simulation tools. The primary package for this is Roman ISIM. The MAST is putting together the Roman archive right now and is just starting to be deployed. There's the Roman Research Nexus, which I'll talk about in just a second. There's a Roman Cal pipeline, which is all the data processing that will occur from what we call level 2 to level 4, but basically the final data products distributed to the community. This is available through GitHub. You can download it and clone it now if you would like and start to play around with it. We, of course, have put together the community defined surveys. So now that these surveys are put together and almost essentially implemented at this point, you really understand the type of data that we're going to be getting over 5 years. There's a Roman community platform, and then there's Roman science collaboration. We have a variety of websites that I can definitely put up and exchange with you guys, right? You can join the Roman Science Collaboration, and then we have a Slack channel. And in that Slack channel, we facilitate questions, proposals. How do we put these things together? And in fact, for this recent call for proposals, right, a bunch of groups who submitted proposals actually got their genesis through the Roman Slack channel. Please know that all data will be public. There's no proprietary period, right? We will get it, we will process it. That will take some time. There will be latency in that, but then we will put it out there and distribute it for use. We will do this via MAST. And then in MAST, you can do your standard queries that you're used to. We also have built a platform called the Roman Research Nexus, and that is directly linked to MAST, and that will allow you to perform data processing with that MAST retrieved data. There will be data releases, right? We'll do this for each of the surveys. And in these data releases, we'll update calibration and reference files. We'll do image co-adding, right? We'll have catalogs of information, so these extracted either spectra or highly processed images, right? PSF, aperture corrected types of images, right? As well as extracted parameters information. So thinking about fluxes, magnitudes, individual line information and characteristics, these types of things. We are going to produce this. And of course, then we're going to accept community contributed products. And I can definitely go into that in detail. But not only are there additional groups who work alongside us to generate higher advanced data products, right? But we're also looking for other community contributions as well. So let's talk about data simulation. So here are kind of like our package of simulation tools right now. We have the ETC, of course, which is the exposure time calculator that's going to help you understand and plan your observations, right? We have STPSF, right, which has been, in other various forms, right? But basically, it's calculating the PSF to high fidelity, right? And it's adapted from JWST. We have STIPS, which is basically a way to kind of, visualize the scene. So basically a pointing where you want to point in the sky and understand how the Roman field of view will correspond and look upon that. And then we have Roman ISIM, which is taking the STIPS to a next level, right? Where you're actually kind of able to generate You're very level 1, so uncalibrated images, so in a simulation type of format, as well as calibrated image products, right? And these are available now through GitHub. You can download them, play with them, so forth and so on. Now let's talk about the Mass Roman Archive. It's spinning up as we speak. We're still working very hard to get it up and running, right? This is a cloud-based archive. As you can see right now, here is a prototype for Roman and being able to search the Roman data. Here's your first user interface that you can see. This is basically customized to looking at WFI imaging data, right? You can actually, there is some data already within the mass to kind of pull from and search from, and you'll be able to perform queries, right? MAST allows you to use all your comfortable AstroPi tools, right? So nothing, there will be new tools and new code, but there's some familiar things that you can at least get your feet wet and you can get started looking at this data, right? There's a cool script that allows you to do bulk query generations, right? There's an additional overlay platform called the DAPI, right? And it's going to be the GraphQL API to MAST, right? And then there are various archive catalogs that we're going to produce. And then finally, I want to highlight the Research Nexus. And I know I'm running short on time, so I'll just wrap this up here. But the Nexus is going to make this possible. You'll have all these terabytes of data, right? How do you even begin to process this? This is not something you download to your laptop. It's just not possible. Even downloading to VMs and clusters, it's going to be just bulky and unwieldy to deal with. And so one of the ways that we thought, in addition to other efforts like NASA Fornax, which is, again, something to think about, Open Universe, various other IPAC-based initiatives, right? There's the Roman Research Nexus right here. So I put up the link right now. It's just launched, and basically it's a way to not only pull the data that you're interested in, but analyze it. So it allows you to do scalable analysis, right? It allows you to pull in software that you have used, right? So you can pull in custom software and use this on the data if you would like. There are also a variety of, built-in packages that you can use to perform data analysis, right? There's a configured Roman environment, so it already sets you up to do computing and analysis right now. There's access to simulated data sets. We're just putting those out right now, but we have simulated data sets for each of the 3 core surveys that I mentioned, right? And then essentially it allows you to do this in a team environment. So you can work by yourself or you can organize a team, and the team will have access to all the data that you pull down as well as how you've begun to analyze it. So we're really trying to facilitate science here. And then I think I honestly run out of time. I was going to go through a whole bunch of other things, but I will go ahead and just leave right here for your view, just an overview of Roman. And just thank you for your time. Thank you for spending it with me. And I hope you're excited about Roman. I really am. Thank you.
Thank you so much, Jen. It was a wonderful talk. Do we have questions? Miro, could you come over here? Any others?
Hello, Jenny. Can you hear me?
Yes, I can perfectly.
Okay, so it was a very informative talk. Thank you for it. My question was regarding the coronagraph instrument and how it is planned to observe, because you mentioned it is a limited time period, that's 90 days. So are the objects already listed and planned, which are supposed to be observed, or does it follow up on the Kepler's telescope field of view?
Very good question. So I think I could have probably given 3 talks. I'm sorry that I left this bit out, but importantly, the chronograph, being a tech demo, has NASA support, but a large part of it is community driven. And this is the Chronograph Participation Program. So essentially, it's just a group of scientists from a variety of different institutions all across the world, and they're really pushing forward both 2 things, right? The organization of how the chronograph will take, observations, right? And what it will take observations of, right? As well as then how that initial data from the spacecraft, once processed by IPAC, will actually be, enhanced and fully extracted, right? So they do 2 types of roles. survey planning and target planning, right? As well as advanced data extraction and product product information extraction, right? And so there is a designated list that has been put together. It's pretty much in its final stages at this point, just because the chronograph will likely be on sky during year 1 of Roman operations, right? So it's going to be first up. And so there is still room. You can join the CPP. There's a mechanism for doing so, right? Once you join, you can get these target lists, right? And you'll see the candidates that have already been selected. Obviously, these stars that we're going to target are nearby, right? They're within a few parsecs, right? We're not going too far out, but still, as a pathfinder for HWO, it's very exciting. So yeah, let me know. Please email me, and I can start to put you in touch with the right people.
Sure. Thank you.
Thank you. We have a question in the chat that don't worry, I remember it. Thaisa asked if there will be other call for proposals besides the one that happened a couple of weeks ago.
So the answer is yes, there will be. We are anticipating at least 2 more call for proposals, right? And so in these in the first call, I want to make a really nice distinction. Not only did we provide support for new data acquisition, but we also provided support for archival analysis, right? So people who want to take either data from a PI driven mission, or preferentially from one of the core community surveys, would do extended data analysis. And so we actually, allow for these types of proposals, and we would support the data analysis, right? Not only in terms of, computing and computing needs, right? But also in terms of people and personnel and travel. So there's 2 distinct kind of flavors of proposals that way. And we also, of course, support theory proposals as well. So there will be another call, probably in about a year-ish or 2. I don't want to be too specific right now. But yeah, please keep an eye out for it. And then again, this is for the 5-year mission. 2 things we greatly hope for. The first is that the chronograph, based on performance, will be extended. It's just a beautiful it's an artwork from JPL, right? It's just a beautiful instrument. So we hope that that will be extended beyond 90 days, but we will see. And the second thing is, depending on our performance at Roman, we hope it will be extended as well, just like Hubble, just like JWST. So we're hoping, fingers crossed.
Thank you. We have one more question from the chat. Mariana is asking whether there's a catalog of low surface brightness simulated data, especially galaxies.
Yes, there is actually. So there is, in fact, a whole sub-working group. Okay, so I mentioned the Roman Science Collaboration. Please join, and I will find ways to get this information to Anna. And by the way, thank you, Anna, for everything. I really appreciate it. I'll get this information, these links to Anna. You can join the Roman Science Collaboration, and within that, you can join one of the various working groups. There's about 4 primary groups, right? And then within those, there are sub-working groups. There's one specifically dedicated to LSB and galaxies, as well as the kind of local, nearby galaxies, right? And in this, they have started to perform analysis. I can even think of GitHub repos that are existing that have kind of been started in these groups, and then, just started to use simulated data. So yeah, we can get this information to you, and you can take it from there.
Awesome. I have one question relating to combining Roman data with other surveys such as LSST. So we are now, every survey is building their own tools, and sometimes it's very hard to unite them. So how do you foresee uniting LSST and Roman data? Because Roman data will be public, but LSST 2 years or 1, and I don't know what's now the norm, but one has to be accessed through the Rubin Science Platform, the other through the MAST. How are we going to get these things working to be able to do the science that we need if we need both surveys?
So this is the $5 million question. Today's economy, it's the $50 million question, right? So it's okay. So you mentioned really key points, right? The first being is that Rubin's data is not completely public yet, right? There are member institutions, member countries, right, that have proprietary access to this data, but eventually it will be released to the public. And there's the rub, right? We are off cycle with one another, right? And so trying to find a coordinated way to even, do data releases is something that we're working on right now. Note that Rubin is spearheaded by what we have here, thank God still, the NSF and the DOE. So it's those are the two entities helping Rubin push forward, as well as a whole bunch of institutions, academic institutions, right? But we are spearheaded by NASA again, so that's kind of a slight disconnect, right? And so how do you kind of traverse those bounds, right? And then the data itself, it's massive. How do you begin to break off a piece of data even, and then do cross correlations and so forth and so on? So it's a work in progress. I won't lie. But what we're trying to do is some of the Roman research nexus has been patterned off of the Rubin system, right, and the data science platform, right? And so we're taking some of the lessons learned. We're hoping that software will be transferable, because the room science platform, for instance, allows for some native homegrown boutique software. Vice versa, we do too. So you could kind of transition. I think the biggest problem, of course, is moving the data around, right? It's going to be just unbelievably hard. We are trying to get money and funding to support this. No, it's a work in progress, and keep fingers crossed. But yeah, I'm sorry I don't have a straightforward answer for you, but please know there are hundreds of people interested in this, and we're really trying to push it forward. And I think the way that gets pushed forward, Reddy, is to take small chunks of data or small areas of the sky, do this kind of external cross calibration analysis, right? Prove its utility, and then hopefully the big funding entities will come and then provide the environments. But yeah, it's not going to be easy. But I'm excited though. God, having that huge bandwidth, yeah, the science is endless.
Awesome. Are there any more questions? If not, let's thank Jen again. And we'll see you in Slack sometime. Bye-bye.
That sounds great. Thank you very much, everybody. Have a good day. Thank you.
Thank you.
So we still don't know what to do with the data.